All right, welcome, friends. We are going to take a look at more circles. In case you can't tell, I'm pretty excited about it. I think it's incredible how we're going to look at circles and how they interact with different shapes. You may not think of other shapes when you think of circles, but today we're going to study how circles and other shapes are related. So our first problems are going to come from section 10.1.3 in your text. It says as you investigate more parts of the circle, look for connections that you can make to other shapes and relationships you've studied so far in this course. So the first problem has us looking at a semicircle. It says, what is the measure of the angle when it is inscribed in a semicircle? So in this case, if QR is 180 degrees, what is the measure of angle P? Well, in this case, angle P has to be 90 because it's half of this intercepted arc that is 180 degrees. But now, because this is a semicircle, if I draw that in, that's a diameter. And now I have a right triangle inside that circle that I can find lengths, find angles, use all my right triangle trig tools. And that's what we're going to do here in part B. At part B, it says you have several tools you can use with right triangles. The special relationship you found above can be useful. For example, in this case, UV is a diameter, which means it cuts through the center of the circle. So this arc is 180 degrees, and I know this angle here then has to be 90. And then it gives me a little more information. It says if TU is 6 and TV is 8, what is the length of the radius of the circle? Well, I already know that that's a 3, 4, 5 right triangle, just multiplied by 2, so it'd be 6, 8, 10. If you didn't recognize that, you could certainly do the Pythagorean theorem to find the diameter of that circle. But it's asking me for the radius of the circle. So if the diameter is 10, I know the radius is 5. And the area of the circle I can answer rather quickly would be 25 pi square units. I can also use the tools that I already have to find lengths of chords. If you remember from yesterday, a chord is a segment whose endpoints are on the circle. Examine the diagram of chord LM in circle P at right if the length of the radius of circle P is 6 and LM, the measure of arc LM, is 150 degrees. Find the length of the chord LM. When I see this here without the arc symbol over the top, I know we're talking about the length of this segment right here. So now I just need to add the radius. I could really draw it anywhere, but it makes sense to draw it somewhere that's going to give me a shape that I know I have some tools that I can use. So I'm going to choose to draw a triangle by connecting the radius from the center of the circle to the edge of the chord. And if I draw both PL and PM, I now have an isosceles triangle, which is a triangle that I'm very familiar with. So now as I take a closer look at this triangle, I need to find the length of LM or the value of X as I put here in the diagram. I know that this arc, LM, the measure of the arc is 150 degrees, so I know this central angle here is also 150 degrees. Now I just have to choose a tool. I could use law of cosines, but that's a little bit more work than I want to do to solve this problem. I can also use the fact that this triangle is isosceles and the symmetry that I know isosceles triangles have to just do some right triangle trick. Now I still want to find X, but in this case I'm just going to find this highlighted portion first here that I've labeled A, and then double it to find X. And I'm just going to use sine to set that up. Either method works, but I think this one is a little bit faster, a little bit maybe more direct, or simplistic in the fact that I can just use some right triangle trig. Now we're going to reverse the process and use knowing the length of the chord to try to find the angle measure. So in this case, I know that the radius have length 5 units and the chord has a length of 6 units. This time I'm asked to find the measure of arc AB. So what I really need to find is this central angle here, and then I know that this arc will have the same measure. So again, the first option I'm going to show you would be to use law of cosines to solve this. So I'm trying to find the central angle. So 6 would be the side opposite that would be the C. So I would set up my equation as shown and then simplify. Be careful here, these highlighted terms are not like terms. You cannot combine them. Don't do it. Instead, subtract 50 from both sides and then divide both sides by -50, which will give you what the cosine of C is. And then to solve for angle C, you're just going to go ahead and use inverse trig to find what the measure of angle C is. Then you can go back to your original diagram. Since C is the central angle, the measure of arc AB would also be that 73.740 degrees. Now that's not the fastest way. That's definitely not the way that I'm going to use, but I think it is a cool thing to be able to solve for the angle in the law of cosine, so I wanted to show you that. Instead, what I would do for this problem is I would use the fact that this triangle is an isosceles triangle, and I would drop that height using the symmetry in there. I would know both of those segments are 3, and then I could find that angle marked x at the top using just sine. Inverse sine gives me my measure for x, and then if I want to find the measure for angle C, I'm just going to go ahead and double that. That is going to be so much faster than using the law of cosines method that I did on the left. So either method, once I know the measure of that central angle is 73.740 degrees, I know that the measure of arc AB, which is what I'm trying to find, is going to be the same as that angle C in the middle. We can also look at chords that intersect inside a circle and look at what triangles can tell us about these chords. So I have two chords that meet at the point E here, and then my dear friend Timothy decides to create two triangles. So we did the same. We went and added segments into the diagram. Part B says compare angles B and angle C. Which is bigger? How can you tell? If I look at angle B here, angle B intercepts this arc AD. So I know angle B is half of AD. If I look closely at angle C, I can see that that intercepts the same arc. So I know that angles B and angle C must be congruent. And if I do the same argument with angles D and A, I can see that they both intercept arc BC. So they would both be half of the measure of the arc BC, which would be the same as each other. So then when I look at these triangles are similar by angle-angle similarity. And when I know triangles are similar, I know that their sides are proportional. I know that pairs of corresponding sides have equal ratios. So I'm going to color coordinate my corresponding sides here. And based on what I have in this diagram here, I can see my different pairs of corresponding sides. DE corresponds to AE because they're both adjacent to this angle that's marked here with the red arcs. BE is corresponding to CE because it's adjacent to the angle B and angle C that we're congruent. So I have my proportional sides. So I'm going to take a minute and I'm going to write a proportion comparing the sides of these triangles. The first pair of corresponding sides I'm going to compare is DE over AE, and the second pair would be BE over CE. Go ahead and use my cross product property and solve this. AE times BE would be equal to DE times CE. And if I look where these segments are in my shape here, I see that AE times BE, those are the two parts of that chord. So their product is equal to the product of the other parts of the other chord. So this is a formula, a theorem that we have proven that we can use when we have intersecting parts in a chord. So now that I've proven this theorem, I'm going to come back and apply it down here. If DE is 8, AE is 4, and EB is 6, then what is EC? So I've labeled my diagram, cleaned it up a bit, and now let's take a look. Because of the similar triangles I have here, I know that the product of the parts of the chords must be equal. So I know that 6 times 4 must be equal to 8 times x. And then solving that is going to give me my value for the missing piece of the chord. All right, we have one more shape we're going to look at that is inside a circle, and that is when a polygon is inscribed in a circle when each of its vertices touch the circle. How are the angles of the quadrilateral inscribed in a circle related? Consider this as you answer the questions below. For the ABCD inscribed in the circle at right, solve for x. Explain how you found your answer. So I have to solve for x here. If I trace the angle that's formed by x, it would be half of this arc, BD. If I look at the other angle here, the 100, 100 would be half of this arc here, BAD, that major arc. So I know the measure of angle BAD is 200, and because this shape is a circle, I know that BCD has to be 160 degrees because the degrees around a circle are 360. So from there, I can find the value of x. X has to be half of arc BCD, so x is going to be 80. Now, as I look at this, I notice that these two are supplementary. Is that always the case? Okay. It says, Alejandra noticed something. I think the opposite angles of a quadrilateral inscribed in a circle are always supplementary. Is she correct? So to start, I'm going to look at this intercepted arc here to go with the inscribed angle A. I know that that intercepted arc has to have a measure that is double angle A. And then the other intercepted arc that I'm going to look at is the one that is formed by angle B. That is this arc here. And I know that that has to have twice the measure of angle B. Now, as I look at this circle, I know that there's 360 degrees around a circle. That arc would have a measure of 360 degrees. So I know that 2A plus 2B would have to be 360. And then using some algebra, dividing everything by 2, I would know that A plus B would have to be 180 degrees. Therefore, I can conclude that opposite angles in a quadrilateral that is inscribed in a circle are always supplementary. So we've done a lot of work with shapes in circles, but today we're going to briefly extend those to look at lines and circles. Now, when I look at lines and circles, one of three things can happen. A line can have 0 points of intersection with a circle, or it could have 1 point of intersection to a circle, or it could have 2 points of intersection with a circle. There are no other possibilities. If a line touches a circle once, it is called a tangent. If it intersects a circle twice, it is called a secant. We will be studying tangents and secants briefly today. We're going to investigate the relationship of a tangent to a circle. In order to investigate it, it suggests copying it with tracing paper and folding it to create the perpendicular line L. For my line of symmetry, I'm just going to draw it here. Because this line of symmetry passes through this point C, I know that these angles here have to be 90 degrees. So I know the tangent line to a circle has to be perpendicular to the radius at the point at which it meets the circle. This point where it meets the circle is sometimes called the point of tangency, right there. And the last thing we're going to do in this video lesson here is prove that the tangent is the line that is perpendicular. It says Ventura began to think about the perpendicularity in a circle. He said, if a radius is perpendicular to a line, how do we know if that line is a secant or a tangent? And then they started working on that question. It says, let's assume the line perpendicular to the radius is a secant. So then it meets it twice. Now, if I draw this triangle here, I know this triangle has to be isosceles because these are both radii of the circle. And then I know if I said it was going to meet at a 90-degree angle, I would have a 90-degree angle there. But because the triangle is isosceles, I would have another 90-degree angle there. Now I said, again, this was a secant. If I'm assuming that this is a secant, I know it intersects it twice. And I'm saying, well, maybe it's the secant that's perpendicular. But as I look at this diagram, this clearly has a problem. This cannot be the case because there's no way I can have two right angles in a triangle. That doesn't work. I'd have too many degrees. This is impossible. Okay, so back at the beginning, we said there were only three possibilities. Either a line crosses a circle, intersects a circle twice, and it's a secant, or it intersects a circle once, and it's a tangent, or it doesn't intersect a circle at all. Because of this contradiction that was shown with my two 90-degree angles, I know that the line perpendicular to the radius of a circle at the point on the circle must be a tangent line. It can't be a secant line because it doesn't work, and there is no other possibility of a line intersecting a circle. It's either a tangent or a secant. Since a secant didn't work, it must be the tangent line that is perpendicular to the radius at the point on the circle.